Welcome to my Commodore 64 Games Memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have Paradroid, published in 1985 by Hewson, developed by Graftgold, and the coder was Andrew Braybrook. Now, I was 12 years old when this game came out, and I think I had it on tape because I did not have a disk drive until much later on. But this was definitely one of my first games that I really enjoyed. Even though I was quite young at the time, I spent a lot of time and effort trying to find out how it worked, and actually produced some early demos of games which looked a lot like it as well. It was a mixture of basic and machine code, and I was working out how scrolling worked and stuff like that at the time. So we have this nice little loader here, and I can see in the C64 debug GUI on the right hand side that we have the memory addresses there going between the drive's kernel and also RAM executed code. So we have some drive code here. We'll have a little bit of a longer look at the drive code, but we can immediately see on the Commodore 64 side here that where the Commodore 64 on the left is doing some bits instructions with DD00, which is the serial port on the Commodore 64. On the drive code on the right hand side is actually doing some processing in the kernel. Not too interested at the moment, it's probably doing some seeking and track reading and stuff like that. But basically the Commodore 64 looks like it's waiting for a signal from the drive to say that the drive is ready, and then once the drive does a store into its 1800, then the Commodore 64 code on the left hand side, you can see there it's starting to go into a little delay loop using the X register and counting down from 7 to 0. And on the right hand side, the drive code is synchronized up with the Commodore 64 code, so we can see that we've got some Commodore 64 and drive code synchronization for sending the bits. At memory address 414 there on the Commodore 64, it's a load X with 3. It then loads accumulator from DD00, which is the serial port, and it shifts 2 bits from the serial port by using the RLE instructions with the 0-page BD there. It does that twice, and then it decrements X and branches on plus back to the top again. So this means that it's doing 2 bits of extraction from the serial port, and it's doing that 4 times. So basically it's a classic 2-bit protocol. The drive code on the right hand side, as far as I remember, was storing 2 bits at a time, as you would normally expect. So the Commodore 64 is expecting to read 2 bits at the time, or at a time rather. On the drive code side, you can see the store A with 1800, and that's at memory location 3244. On the right hand side there, again, you can see the load accumulator with X with 3 in the drive code as well, and that tells us that it's going from 3 to 2 to 1 to 0, and it's sending 2 bits at a time on the drive code side, which again is what you would normally expect, because you want the drive code and the Commodore 64 code to be in sync. As the drive code sends 2 bits of data, you want the Commodore 64 to be reading that 2 bits of data. And the synchronization between these 2 bits of code has to be quite precise. You don't want too much variance either way. This is usually why the screen is turned off. You don't always have to turn off the screen, but the thing is that the Commodore 64, due to the way that the VIC chip pauses the processor every now and again, every 8 raster lines basically, you want to try and avoid the times when the VIC chip is stealing cycles from the processor. So the easiest way of doing that is switching off the screen. Switching off the screen makes the VIC chip stop stealing cycles, basically. The drive code on the right hand side there at memory address 31C does those 2 ASLs and then an ROL, and ASL and ROL. Again, that's just calculating the 2 bits. And we get this nice little stripy pattern, and then the load has completed. Now the reason why I'm using the C64 debug GUI here is that in memory there you can actually see, look, there's a whole bunch of text laid out right in the middle of memory there, probably starting from 8000. This is the text which scrolls up through the title screen and track mode sequence. There's quite a lot of text. That text seems to be decompressed from elsewhere in memory. Probably it's using some text stored there or some other compression. But basically this game is great. It actually tells you the instructions if you are going to sit around and wait to read this in a nice easy way. So if you don't quite have an original copy, although I had an original copy, but if you didn't, then you know the game would give you the instructions anyway, which was useful. But I had this on tape. If I remember rightly, it was probably bought from John Lewis in Bath Spa in the UK all those years ago. Because, you know, John Lewis back then used to sell Commodore 64s and computer games. So this split here, back in the day when I was really young, intrigued me. This was one of the few games which had a decent split, although the split on the screen was wider than normal. Actually, it was a little bit more stable than other games. A lot of other games, the black split of the screen would bounce up and down by a raster line, but if I recall, this one is a little bit more stable. So as I'm looking at this in the C64 debug GUI, I can actually see that the screen is not being disabled by selecting the invalid character mode. If I move the little targeting cursor up and down over the screen display mode maintains standard text there all the time. So you can see there that standard text is enabled. It's not in the invalid display mode, which is normally used to switch off the screen entirely. This means actually that we have a nice little red bar between the score panel, or a background color bar between the score panel and the main game display area. Now I'm just moving my player character around, and one thing to notice is that as I move the player character around and as the other sprites move around, you can see actually that the sprites move around quite considerably outside the screen boundary area as well. So the little red boxes of the C64 debug GUI that I'm using here, the red boxes are configured to actually show around sprites, even when the sprites are underneath the borders and underneath any invalid screen display area and stuff like that. Because the red borders around the sprites are basically drawn according to their coordinates. It's not drawn according to whether or not the pixels are actually visible, which is useful for us because we can see how long-lived the sprites are. And as I scroll around, you can see actually that the sprites, there's an enemy sprite there, and it's actually active for quite a long period of time, with the sprite in the debug view moving all the way over the score panel. Look, eventually it gets removed as I think the dead enemy or the idle enemy routine probably catches up at some point and then removes that sprite from being rendered in the active VIC display registers there. But basically, yeah, these sprites are not cold, if you like, from the screen edges, or rather the game scrolling area. They're actually cold with a much larger rectangular area around the screen by the looks of it. So in this mode, this is like the one of the other debug screen editing modes, if you like. Now, as you can see there, the split is actually has a how can I put it? A gap between the bottom of the split and when the sprites become active compared to when the characters are active. There's actually a little pixel line. So that tells us how the sprites are being updated. The sprites are basically being updated probably with their sprite frame values being redirected to a blank sprite frame, which is usually the normal way of doing it. Because the sprite frame values, which are the sprite values which are stored at the end of the characters in the screen bank, those are fetched every scan line, but they're actually fetched quite a bit later during the scan line draw. So if you set them during one scan line, they will actually only tend to get drawn by the VIC the scan line afterwards. It's something that you have to keep in mind because it needs a little bit of extra time to fetch the pointers, the frame pointers, and then to fetch the actual sprite data that it needs to render with. When we're in the informational screen, the screen split is still active, look. But it's definitely using two character sets. So there's the character set which is being used during the split, which is, the character set is actually at 4000 in memory that I can see there on the right hand side in the C64 debug GUI. But then in the information screens here, it's using the same character set for the bottom area as it is for the top score panel. Also notice the little red sprite bounding boxes there. We can see that the display for the ship graphics and the player graphics and the alert system and the alert status and stuff like that, it's actually using sprites. This helps to give a little bit more variation in terms of graphical variations of color for this screen, which I thought was a nice little touch. So here, as I'm scrolling the little targeting cursor along to the right, it advances each cycle, and we can see the instructions on the left-hand side that are being executed on each of these cycles, and we can see that it's doing a load from a memory address and then storing it into, say, for example, 4B FB, 4B FA, 4B F9, and these are the sprite frame or sprite frame index pointers that basically tell the sprites what frame to, or what graphical frame to actually render for each of the VIC sprites. Now here, at this point on the screen, the sprite pointers are all pointing at 4000, look. The sprites, or at least some of the sprites, are enabled, but all of the sprite frame pointers are set to 4000. The display is still on. The display mode is still standard text. But the pointers are being updated at this point, which basically tells the sprites to start displaying data, but the sprite which is at 4000 is completely blank. It's only at this point when the sprites start displaying graphical data when the sprite frame index pointers have been set to other values. Now that's the usual way, that is definitely the usual way of turning effectively the sprites from being invisible to being visible with the graphics data that you want. Okay, the way that the sprite graphics are actually rendered on the Commodore 64 means that you cannot enable the sprites halfway down by updating the enabled or disabled flag. You have to do it by setting the frames, and sometimes people or games would set the sprite horizontal position as well, so that they were all hidden by the border, for example. But this one doesn't, it just uses the sprite frames. It's interesting to note here that although the sprite frame numbers are the same, the sprite pointers, it's actually the sprite graphics that we're updating as well. So let's have a little closer look at that in the ICU64 debugger, because I think that there's a little bit more graphical detail in there that ICU64 can show us compared to what we could see in the C64 Debug GUI. I tend to use C64 Debug GUI because it shows very well where the sprites are with those nice little red bounding boxes. But if I want to have a look at the broader memory picture, then I use ICU64 with its broader memory debug view, because the memory debug windows and stuff like that show a larger section of memory than the smaller display centered piece of memory that the C64 Debug GUI actually shows. So here we are in my other favorite tool, ICU C64. I've already opened the memory view there. This is the monitor window. I'm just having a little look at the disk directory, and it just contains one file. We are watching the turbo load, the 2-bit protocol disk transfer load come along. We can see immediately that the graphics map view there in the middle of the screen at the bottom is showing the sprites at bank 4000 in hex, which is the second VIC bank. We can immediately see that there's quite a lot of sprites there. Now this is interesting. I can see in the graphic, in the memory debug view there, a very large green rectangle there on the left hand side. Note that when the screen starts scrolling and it introduces this extra text, the green rectangle is shifting down through the memory view. Green indicates reading memory. So this tells us, that green rectangle tells us that the memory is being copied by reading, and then the bytes are being read by the CPU and then stored somewhere else for the actual displayed VIC bank. I'm just using my updated C1541 disk tool here to see if I can find any extra file data from this G64 disk image. The C1541 tool I updated to basically scan through and see if it could find any hidden blockchains, because the drive blocks are stored in a linked list arrangement. But I'm looking through this data here and it doesn't seem to be that interesting. They all seem to be single blocks in length mostly, apart from the disk directory, which was at track 18 sector 0. So there's nothing really interesting there that I could extract. But we can see here again, in the memory debug view in ICU64 here, this whole memory view is 256 by 256 pixels. That means that every single pixel corresponds to 1 byte in the Commodore 64's memory, because 256 times 256 is 65,536 bytes. Now this large green rectangle is basically displaying a whole bunch of scrolling data inside this very large chunk of memory there. It's basically at 8,000, probably by the looks of this, all the way to C000 in hex, or rather 8,000 to be FFF, which is the third VIC bank. So the screen scroll, if we zoom in and check the memory addresses, we can see, yeah, look, the screen scroll is at the moment, it's reading around 848C, A48C. Up here, it's reading from 8 to AA, which is up at the beginning of the third VIC bank, sorry, which is at 8,000 to BFFF. And if I warp through, you can see very clearly the pattern of reads that is going on for this green rectangle, which shows CPU memory reads there. It's showing that it actually progresses down and then hops across to the next column in the memory view and then scrolls down through that as well. So we can see very clearly that the text here has a certain layout. If we use CharPad, what we can do is that we can use CharPad to import the snapshot from ICU64. So ICU64 uses Vice, and saving a standard snapshot file from Vice means that we can then import it into ICU64. Into CharPad, from ICU64 into CharPad. Now we need to No, I don't think we need to enable tiles. I think it's a character-based screen, obviously, because it was copying that size of bytes from a virtual screen, if you like, in memory to the actual screen. So what we need is that we need to set the tiles mode off, multicolor mode is off, and we'll have the coloring mode on with per character turned on. Now we can assume that the map width is 256 pixels because that's the width of the memory view, and each pixel is 1 pixel on the memory view, so it's 256 pixels wide. We need to set the character set to the right memory address, and the right memory address of the character set to use is from here, and that is the character set at 7,000, so we'll set the character set at 7,000, and the map we need to set at 8,000. Oh yeah, what we do need to do, of course, is that we need to open snapshot first, otherwise we're not going to see anything on the screen at all. Whoops. So there we go. Right, so we have the character set at 7,000, and we want the map at starting at 8,000 in hex, and there we go. We're getting some of the text, but the text is all kind of like weird character colors. Now, games usually use some kind of like lookup table for the text colorization or the graphics colorization. Basically, each character would tend to want a color being written into the color RAM, and we can see here on the memory view, on the debug memory view, that this yellow bar on the right hand side here in this little subsection of memory indicates memory writes. Now memory writes are shown as color yellow, and we could see the memory address there was at D800 to DC00. So we'll put a little watch point for the store at D800 to DC00 in the monitor debugger there. Now when you want to open the monitor, it depends on your version of Vice, which key binding you have and which you've configured, so you use whatever that is. But basically here we can see that when it's storing to the color memory, it's doing a load from 800 in hex first, indexed with X, and X comes from the accumulator value, which is basically the screen character byte, which is being transferred from A to X. So the game and the title screen scroll for the level map, if you like. Well, the title screen is showing a scrolling screen, but basically the game also uses the same area of memory, if I recall. But basically it's using a color index lookup. So I'm just putting these notes into the Paradroid.txt file. I'll be, of course, as usual, committing this Paradroid.txt, the debugging notes text file. I'll be committing it to source control so you can see as well. So the character set that we're currently looking at is at 7,000. The code that was doing that is at 399E, and that's where the colorization is. That's where it takes the byte of the character and then looks up the corresponding color byte to store into the color RAM. The color RAM on the Commodore 64 is special. It's 4 bits wide for each character cell. It's not the full 8 bits. The RAM underneath it is 8 bits, and you can choose whether or not you're writing to color RAM or the RAM underneath, of course. And you control that using the one address in 0 page, which is the processor port, basically. But here we know that now we're getting the color index lookup table from 800 in hex there. So we can set that there, and then we click OK, and this allows us to then easily see in CharPad the full screen. Now we can see that it's not a height of 100 characters. If we use the selector here, we can see what the coordinate range is, and that's basically 63 or 64 character rows. So we overestimated the height of the scrolling area by a few character rows. So it's 64 characters rather than 100. That makes sense because 256 times 64 is in decimal. Those are numbers in decimal, but if you convert to hex, it's 4000, which is 4000 in hex. And 4000 in hex is the size of one Vic bank. So basically the area of memory from 8000 all the way up to C000, not inclusively, or exclusively rather, is basically this map area which is scrolled around, and we can see the whole thing there. I think I'll save this CTM file as well into the debugging details directory and then commit it to source control as well, so you can also see what these graphics are during the title screen. So into the game, and we see that familiar green rectangle there, but look at the memory view there. We can see what looks like little green lines moving around this map area. There's also these little green lines, so it looks like the targeting for the enemies actually does a whole bunch of reads into the graphics map area. That's really interesting. We'll have a little look at that later on. But basically the screen split for Paradroid is actually a little bit unusual. Instead of turning the Vic into the invalid text mode and having a black bar, if you like, which is basically a side effect of turning on the invalid text mode, is that the Vic doesn't display anything at all. You have to do some special stuff with sprites and stuff like that, but still it doesn't display anything for the character screen. Instead it's using the character set of 4000. We can see in the graphics map, in the debug window in the bottom left hand corner there, that the character set is practically all filled with 0, which is completely empty, which is what makes the screen split unusual, is that the sequencer, the Vic display sequencer, is still enabled. We saw that in the C64 debug GUI, but ICU64 is confirming that for us. So I'm just noting that down again in this debugging text file here, so you can refer back to those notes later on. Now I'm really intrigued about those green tracing lines, and look, there's little yellow lines, yellow blobs. Now the yellow blobs, remember, in the graphics, in the memory view there, indicate memory writes. So those yellow blobs there are updates or writes into this map data. Pretty sure it's the doors opening and closing, but I really do like these green tracer lines. So look, when the enemies are considering whether or not they want to fire at you or move towards you, probably firing at you, there's probably doing a line of sight calculation by reading the individual pixels, individual byte values which correspond to characters in the graphics view there. Just quickly before we have a look at for the code for decompressing the map data, I just really wanted to show a little bit more footage of busy areas of this map. Look, when there are lots of robots, look, we can see that there are lots of green lines going on for targeting of the player. There seems to be quite a lot of reads going on in a circular fashion around where the player is. That's probably for collision detection. To demonstrate the enemy reads for the collision and also the enemy firing a little bit better, what I'm going to do is that I'm going to remove the memory reads for the scrolling routine, for the screen character data scrolling routine. So here up at 3996 is a load Y with 26, which is where the loop starts for copying a horizontal row, and then it ends at 3985 there. So I'm going to circumvent this code by just inserting a jump at the beginning where that load Y is. This is in the middle of the scrolling routine, so we can just remove this by jumping straight to 39A7. This basically still runs all of the code for updating each row start address and stuff like that. It will just avoid doing the 40 bytes or 39 bytes of horizontal character copies. I'm just setting the register to equal, Y register to equal 0, so that it doesn't run around the loop anymore with that branch on plus at 39A5 there. So if you have a look at the disassembly, the 3996 instruction is now jump to 39A7. 39A7 is load accumulator with $1C, which is the start of the calculation for updating the screen's row address. You can see it adds on hash $28 there, the immediate value of 28 in hex, which basically adds on 40 characters. 20 is 32 in decimal, and 32 plus 8 is 40. Yes, so it adds on 40. 28 in hex is 40 in decimal. Now you can see here very clearly now the lines from the enemies, and I've zoomed in on the memory view here so you can see them even closer now. You can see the horizontal and vertical lines as the enemies move around, but you can also see what look like diagonal lines for firing solutions. For when the enemies get close, they seem to send a little targeting line towards the player. Now don't forget that the scrolling for the game is now disabled, so even if I move around, you're not going to see the characters for the map data scroll around. But basically I've removed that confusing large green rectangle, which was indicating that the code was doing a lot of reads from this memory address. So the remaining reads and the remaining writes are entirely to do with the enemy AI. So you can see when the enemies get close, you can see we've got these little rubber band green lines appearing. Now, the lines will be bright green when the reads are just done, and then they will fade out to black as the memory reads age frame by frame. So you can see the way that the enemies move is that before and after, and actually on their position, they are checking the characters ahead, and probably maybe the characters behind as well from the direction of their movement, or maybe two characters ahead to see if it's really clear. Don't forget that the tiles in this map are 4x4 character tiles, so it might be looking up to 4 characters ahead. That might account for the horizontal line, because these lines are what, 2 or 3, they're 3 or 4 pixels long. You can see that circular kind of like, almost looks like a large butterfly centered around where the player character is. That's probably the player character collision. If I zoom in to the sprites view here, you can see, look, the sprites when they animate are actually animating the frames by updating them dynamically in the memory as well. So usually what you do is that you would normally update the frame index value, and it's only 1 byte. But that would need an awful lot of sprite frames if you have a lot of robots on the screen at the same time. So what this is doing is that it's cutting down on the sprite memory by basically calculating dynamic animating sprites. We can see that when we go into this information screen as well, that the top of the character set memory and correspondingly the sprite memory in those graphics maps views there is actually being filled in with something, and that's okay. The screen split doesn't need to be clear if it's not scrolling the screen area. So the game has stored some temporary data there. But I just saved the snapshot there because if we load the game from that, if we load the second snapshot, we'll be able to look at the current rendered map as it is in the game. So if we set the character set now back to 7,000, and the character attributes table was at 800 in hex, don't forget, and we're assuming that it's the same, pretty sure it is. The map starts at 8,000. But of course the character set doesn't use the score panel character set, it uses the game character set, which is at 7800 in hex. And there we go. We've got the entire map data there for this current level. So that's useful to know, isn't it? Is that if we wanted to extract the level data, we can use Vice, and we can use the ICU 64 version of Vice, or we can use any other version of Vice practically to get to that level in the game, and then to save a snapshot, and then to import that snapshot into CharPad and then extract the graphics that way. So it's always nice being able to extract the graphics, but this is only extracting the graphics for the currently visible level. Wouldn't it be really nice if we could extract the graphics some other way? Well, to do that, we need to see what is storing or decompressing memory into this large area of memory between 8000 in hex and C000 in hex. So we need to look for this kind of routine which decompresses map data. So that's what we'll do next. In the debug memory view, that when I change levels between the lift by moving the lift up and down in this lift shaft and going between different decks, we can see that there's a whole bunch of yellow writes, and yellow indicates writes to this area in memory. So we can see that there's a whole great big bunch of memory writes. So we know that the code is decompressing a lot of data or rendering the map in some way. It may or may not be compressed as such. I mean, it depends, right? I mean, sometimes it makes sense to use a compression algorithm on graphics data. Sometimes it can be just an uncompressed map, but it uses memory blocks. It uses map tile blocks, rather, sorry. Blocks in memory which are map tiles. So, say for example, the value of 0 will extract a 4x4 character block from memory and then store it, and then the value of 1 will extract a different map tile which is 4x4 character blocks from memory and then store it. Using map tiles is quite an efficient way of compressing the memory itself, or at least partially compressing the memory by storing a smaller number of bytes and extracting a larger number of bytes is technically compression, but it's not full compression. Anyway, this routine looks like it's the routine which stores into the map area, the uncompressed map essa, because I put a watch point for store at 8000 there. We can see this routine here. Look, the routine at 35EA, look, it's doing 2 counters with an X and a Y, from 3 to 2 to 1 to 0, so that's 4 characters horizontally and 4 characters vertically. The inside loop is the horizontal loop, and then the outside loop, which is with the X register, is actually used for the Y values for the 4 different rows for the map block there. But yeah, we can see quite clearly and plainly that that's basically doing a load indirected using indirected memory addressing from 1.2 in hex, and then it's doing a store to 1.4. If we have a look at the memory at 1.2 to 1.3, we could see that the memory was pulling values there, which is basically the blocks. We can see, look, groups of green reads repeatedly and also sequentially going through, depending on which which level is being rendered into that map view or map memory there. We can see quite clearly that it's doing repeated chunk reads from certain memory addresses, and it's doing a sequential read as the green line progresses across. So we can deduce from that it's reading chunks of map tiles, and it's using the map tile indexes as a sequential read from a different area of memory. So we can note down now where we know where the 4x4 character block draw is. We know that character blocks are colorized using that lookup table, so we don't need to worry about having separate colors for each of the map blocks. We just have one lookup table for the character cell or the character code rather, colorization lookup. So where does the actual tile index get calculated? Well, it's just above here. We can see that there's a whole bunch, there's an AND with one F there, there's a couple of shift rights and then rotates. That basically does a multiply by 16. And the AND with 1F basically restricts the range of the tile indexes from 0 to 1F, which is 0 to 31 in decimal. But basically it's taking a number and then multiplying it by 16, looking that up into the tile memory, because each tile is 4 by 4 characters, which is 16 characters, so it needs to do the multiply by 16. If we have a look at the CPU history here in the monitor debugger, we can see that it's actually loading. Well, these two memory addresses are loading from F100 and F110, and it's storing into 1A, 1B. Then here, look, at 35AA, it's doing a load accumulator indirected with 1A. If it's plus, it just goes straight through to 35C3, which seems to render one block. But if it's a negative value, then it seems to be reading a count. So basically the map looks like it's run length encoded data. There is a character block index, or a tile block index rather, sorry, a tile index from 0 to 31, but if the high bit is set, that makes it negative, and then that tells the block draw routine to draw repeatedly that many number of blocks from the next byte in the run length encoded map data. So it's a Paradroid, we can definitely confirm, is using run length encoded data for its maps, which for the time when this game actually came out is actually a really cool idea. It probably vastly reduces the memory being used. The load address, the load accumulator with F100 and F110 there just above and storing it into 1A and 1B in 0 page seems to take the Y index as a level index number, and then it basically seems to have a low byte, high byte load and store into those 0 page addresses, which is used for the indirected memory address load. We can safely assume that. The fact that those data tables at F100 and F110 are 16 bytes apart, in other words 10 in hex bytes apart, then we can safely assume that at least for this part of the game, there are up to 16 individual levels here. Look, F100 to F110 is definitely 10 bytes, which is interesting. So there are up to 16 levels, or 16 separate maps, rather. So I'm just adding these little debugging notes into the debugging text file here, so you can refer back to them later on, and actually so I don't forget. And I'm just noting down here what I think is the algorithm being used for the run length encoding, which is if the byte is positive, then store the map tile once in the map data area of memory. And then if it's not positive, then read the next byte, which tells it the count of tiles to actually render, just making sure that that's what it is by looking at the code. So when wanting to reverse engineer games like this and to find out how they work, and to try and extract, well, you see what I'm doing here is that I'm looking at the code to try and understand how I can extract individual maps easier than having to play through the game and visit the maps explicitly. So there are roughly 3 ways of working through the map data to get at it. One is playing through the game and having a little breakpoint on this routine, which will enable me to manually save out the map data from 8000 to C000 manually. And I can do that by having a breakpoint in the debugger, and then I can just visit in the map. I can visit each level using the lift shaft, using in the game lift shaft. But that means that I'd have to navigate through the whole game effectively by scrolling through each of the levels and using all of the relevant lift shafts in the game to make sure that I could visit that. The other way of doing it is that this routine seems to be reading the level index into the Y register and then using that to index, what was it, into the F100 and F110 memory address range there. So it seems to load Y with 33 from the 0 page, right? So I could, in theory, change the value that's stored in the memory at 33 and then cause a different level to be decompressed by having a breakpoint in the monitor there to basically allow me to intercept the level and then rejiggle the value for telling it to decompress a different level. That's the other option. But that involves some manual tweaking, right? The other way is to use some kind of automation for helping to automate this work, which would be potentially a lot quicker to execute, although you need to author the automation to do that, and you can author the automation by sending remote monitor commands by connecting to it via the remote monitor. You can certainly do that too. And the last way is to finally properly understand the data and then extract the data by writing some code to extract the data yourself. And that's one of the last ways that you could do it. So when you're reverse engineering, you need to do a what I like to call a cost-benefit analysis of the different methods, how expensive, how reliable they are. It's expensive to use manual effort, and it's a little bit unreliable if you have to do it for 100 levels. But is it a little bit more reliable if you've only got 4 or 5 or 8 or 16 levels? Yeah, sure it is. So, maybe the risk of doing it manually is acceptable compared to trying to author some automation. But it's not very repeatable, right? Whereas if you use automation, then if you write the automation well, then it's a lot more repeatable to use automation, and it's a lot less risky, but you have to invest quite a bit of time and effort into creating the automation in the first place. So it depends on how many times you are expecting to repeat these actions, right? So we can see here, as I go through the lift shafts, if I move up and down in the lift shafts here, we can see at this breakpoint here that the Y register changes from 4 to 5, back to 4 again, as it's decompressing different level data from its, as we now know, run length encoded map data. So if I move down, it's got the Y register equal to 6, and then Y register equals 7, and I'm moving down to the lift shaft, and it's now 9, and so on and so forth. And this is what we get from being able to use a lovely debugger like we have in this version of Vice. It's certainly a lot easier to use a debugger and get all of this information. Information is key when you're trying to debug or reverse engineer, especially somebody else's code. It helps greatly when you're trying to debug your own code, but it helps even more when you're trying to understand somebody else's code. So let's use the monitor to switch to the RAM bank and to make sure that we save out the whole of memory at this particular point in time. So if we want to use this whole memory dump later on, we can. So I want to save from memory address 2. I don't really care about the first 2 bytes, and actually a PRG file has 2 bytes of header anyway. So the 2 bytes of header is used for the low and high byte of the loading address anyway. That's just a convention for PRG files. So I'm just skipping the first 2 bytes so that even if I load this as a binary file later on, all the way from the start of memory, then the memory data offsets and the file data offsets are going to be the same. Let's just quickly confirm here what memory is actually a F100 and to F120, and we can clearly see low and high byte addresses into memory. This first byte pair shows us that memory is at F249. The second byte pair is the memory for the map is at F289. So on and so forth. So we know definitely that that's low and high byte tables for the run length encoded map data. From the CPU history, we saw that the code at 2727 in hex there in memory actually just does a little JSR to 3590 and then an RTS straight afterwards. So that seems to be a little bit of setup code there. And then basically if I switch the character sets graphics map view there, we can actually see, look, because the character sets have a certain memory alignment in this debug view there, we can see basically the whole of the VIC bank as a whole bunch of character sets, and we can see that the maps change as I move up and down the lift shafts there. Now, if I change memory address 33 to be a different number as this routine is being called, then 0 page memory address 33 seems to have the current map to decompress. So it looks like I can teleport myself around the maps by overriding the current level map number in the decompression view, which is useful to know, right? And the rest of the game seems to handle this unexpected teleport to unexpected levels actually quite well. So let's go back here into the, there we go. So let's change it so that I'm always going to decompress level map 0, okay? So let's, there we go, you can see level 0 is the top of the ship. It's these 2 very small little areas. Right, so the top of this ship, if you recall, if you play this game, contain 2 very small little areas. There's this area here, and then there's a little separate area which is like the top bridge area, if you like, of the entire spaceship. I guess that's what it is. Or maybe they're observation domes or something like that, right up at the top of the spaceship. Anyway, it means that we could, if we wanted to, circumvent the level decompression code to decompress whatever map or level that we wanted to, just by overriding this memory address here. And there we go. Now I've managed to get the player character, look, my little player robot is now outside of the main map area now. Isn't that funny? I'm wandering around in the spatial void outside this spaceship. So yeah, that's all useful information that we can use now to try and circumvent the rest of the game. So the game map decompression code, we can use all of this debugging data that we have to try and circumvent that code for our own purposes. So one of the ways of doing that is to use some automation for controlling the Vice monitor commands from an external network connection, which we can certainly do and I'm using my BDD 6502 Qx Plus framework here, which contains some human readable syntax for creating basically feature files and test scenarios, which allows me to automate the coding or the testing and coding of my code, but also reverse engineering other people's code and games. And we can use this with the Vice monitor here. So I'm taking the Exile feature, which was basically used in one of my previous videos, the Exile video for automating the injection of Sprite decompression or Sprite frame decompression code into Exile as it's running. I'm now taking that and I'm changing it to basically create this new Paradroid feature file, which will allow me to automate Vice via its remote monitor debugger to allow me to set breakpoints and then change code. Now I'm going to be debugging for a while, so I'm creating this little montage here of all the steps I went through while debugging this, because it took a little bit of time and effort to actually figure out how to cleanly get at the code that I wanted to get at. So here's a nice little montage. So after debugging a little while, I finally figured out what my problem was. And the problem was that I wasn't quite using the right debugger commands in the monitor. I forgot that if I execute a go command to execute the decompression code, I need to have a breakpoint after the decompression code for the map data completes. Otherwise the game tries to run at that particular point in time and it just continues on and then doesn't allow me to then save data and stuff like that. So once I figured that out, this is what the automation code looks like now, is that it basically sets the initial breakpoint and then I wait for the remote monitor to, or the machine code monitor to hit that breakpoint at that memory address, and then I set up some other breakpoints. But basically what I do is that I use the remote monitor command to then basically send a memory update command, which is the right arrow there, sending data to 0 page memory address 33, which from the debugging notes is the current level number, and then basically I use the automated syntax here to automate the sending of a go command, well, setting the current level number and then sending a go command for 2727, and then once that completes by returning to the breakpoint at 272E, then I can send the remote monitor command to save the block of memory. And this will trigger once the game tries to decompress the map data. Okay, so here the test scenario is basically automating the opening of Vice, and it's automating the loading of the game, and then it's saving the decompressed memory chunk by using the monitor save command. So if I basically I put a breakpoint in the map decompression routine, so that when the map decompression routine triggers, I then start calling that routine with my own values, which then allows me to choose the memory, to choose the map that I want to decompress, and then I can choose to save that memory as raw data. Now, and then I can load the raw map data as the decompressed map data, and I can use that. I don't have to re-import the full snapshot anymore. What I can do with CharPad is that I can just import the map data as a raw binary rather than importing the whole snapshot, which is useful because then I've disconnected the character set from the decompressed level map data, which is useful that if we wanted to, which I'm not going to want to, but if anybody else wanted to, then they could extract all of the level map data like this. So here I'm just giving a quick example of how you can use the same commands to basically save out level 0, 1, and 2. Nice and quickly and easily by using this automation syntax. And actually, let's expand it a little bit more as well. So instead of just level map level 0, 1, and 2, let's extend it to include a few extra levels as well, just to really prove the point. So that there's level 3, level 4. Don't forget that we're counting from 0, level 5, level 5, and level 6 there. So actually we're saving out levels 0, or map levels 6 to 0 to 6. So that's actually 7 files, right, in total. So Vice has opened there. I'm just clicking on it to maximize the window. There we go, getting into the game, and then it just quits because I've circumvented the map decompression code to save out those separate level data files. So without importing the whole snapshot, just using the binary map data import, I can, say for example, choose to load level 6, which is actually level 7 in reality. 0 to 6 is level 7. Looking back at the map decompression and tile drawing routine here, we can see that with this add with carry E8 at 3.5 E6, that seems to tell us actually that the 4x4 map tile data actually starting at E800, and we have 4x4 characters for each map tile. So if we use this information of the low and high byte start address for the compressed RLE compressed map data, and also the start address for E800 for the 4x4 map data, block tile data if you like. The terminology of tiles and blocks can be basically interchangeable at this point, but basically map block or tile data starting at E800 allows us to actually consider writing some code to decompress all of the RLE compressed map data and then to load that into CharPad as well. So if we set up another Vice snapshot data import and we open the snapshot that we opened before, and we set up the character set, and we set up the character attributes lookup table, and we set the tile set data at this time to be at E800. Now, because the map data is RLE compressed, we don't really care what map data we tell Vice, we tell CharPad to have a look at, because CharPad doesn't, or at least this version of CharPad doesn't have an RLE decompression mode. So we'll just leave the map data pointing to somewhere in the map. Doesn't really matter at all. Don't care. So if we click on OK, and then we have a look at the tile set data, we can see, look, well, we have a maximum of 32 tiles, not 256, so we need to take that into account. The colors are also not entirely correct, although they were correct, I think, but we'll set up some suitable colors to make it a little bit more visible. Set the quantity of tiles to 32. That makes it a lot easier to see. The background color will set to be light green, for example. Bing, like that. That makes it a whole lot easier to see. So we can see that the game uses these 32 tiles by CharPad extracting the tile data, which is stored at E800 in that Vice snapshot. So wouldn't it be nice to use the RLE uncompressed, the run length encoded uncompressed map data with the tiles instead? It would be a lot more efficient, right? And it would actually allow CharPad to represent the game data for the maps a lot more accurately and efficiently as well, because the map data we use is tiles rather than having huge, great big areas uncompressed in memory. So we really should try and create some code to compress that RLE, compressed map data, using the tile indexes instead. So we can do that. But what we need to do first is that I think we need to save this working file, because we know that the map tile data, right, is good. So we'll just save that as a nice little working file. We'll call it, like tiles mode, I think, just to make it obvious what the data is. But we need to have the proper map bytes now. So to do this, I think we'll probably use Python. That's why I am starting PyCharm. So we'll write some quite simple little Python code to read in the saved chunk of memory from Vice, and then we'll tell that to uncompress the data and then store out uncompressed bytes. So bear with me for a minute or three while we type in that code. Python is a good choice for this because it's a good language. It's relatively simple to use and relatively simple to start up and to debug. Although practically any other language could be used for this purpose as well. You could use whatever language you prefer, C++ or Java or whatever. So here we are. I'm saving this as paradroid.py, and that's going into the debugging details source code repository. I'm just sketching out some code for what I want it to do. If you're a little bit familiar with Python, then you can see at line 3, I'm just doing a file open. Line 5 does a file read of that data, basically is data, bytes data. I then want to have output data, which I'm initializing there at line 12. I also want to have like a little file offset thing. So what I'm doing is that I'm basically trying to re-engineer what the 6502 code was doing, the Commodore 64 code, but I'm just re-engineering the functionality and the behavior as best as I can in Python. So the level offset was calculated by reading those low and high bytes for the memory offset at F100 and F110, right? So if we check what those values are here, we can see that they are correspondingly the same. So there we go, there's the low bytes, and then there's the high bytes for the memory address, which is basically the same as the offset into the file data, which is the same as the data that we have here in the debugging text file details. So the Python code needs to take the current level map number and then look up the memory address offset, which is the same as the file offset. And then the Python code will take that into account when processing the run length encoded data. So we'll just take a hex value of F100. 0x as a prefix basically says use a hex value, and we're using the hex value of F110 there. We want to offset this by level num, which is a value from 0 to 15 in decimal. And of course, the low and high byte addresses need, the high byte address needs to be shifted up by 8 bits. That's what the left arrow with 8 means, is that it shifts it 8 bits to the left. So it's not file, it's data, which is the binary data that's been read in from the file. And of course, the file name needs to be correct as well. It's not t.bin, it's pd.prg, which is paradroid.prg. And if I print the hex value of this level offset by using the hex helper function there, and then if I run that, we can see F249, which is the low byte, high byte value there of the memory address or the file data offset. So we know that level offset is correct. So we need to start reading the run length encoded map data from the file offset that we've just calculated. So the run length encoded decompression code rather now is going to be decompressing values into out data. I want to decompress a maximum amount of memory. So we're having a little while loop here. I don't need an integer value, actually. I can look at the length of out data. So I want the current data byte that's being read from the compressed data, which is going to be data indirected with level offset. And of course, level offset needs to be incremented. The problem when hopping between Java, C++, and Python is sometimes remembering how your increment operators work. There we go. Right. So if the current byte ANDed with hex 80 is equal to 0, then we will just, I think, output the byte value without any repetition. So we'll just append on the current byte to the out data, and we'll only do that once. We'll add in the little AND for 1F, which is what the Commodore 64 code was doing. And if it is negative, then we want to have a repeatable number of bytes. Actually, we could reproduce what the behavior of the C64 code by always setting repeat bytes to be equal to 1, and then if it is negative, in other words, if AND with hex 80 is not equal to 0, then we'll read the repeat number of bytes. So we'll do the code that way round. So then we can just have one loop which does while repeat bytes is greater than 0, then we'll do the out data append, and then we'll do the repeat bytes like that, I think. A list object has no attribute of len. That's, kind of true, but we can calculate the length of the out data by doing that instead. And there we go. So then I write the out data as binary data, and if I take the current map and I import the decompressed map data as a raw binary blob, then let's see what we get. And I called it ctemp out out0.bin, right, which is the current level number. That's intriguing. What's going on here? The level data doesn't seem to be quite correct, although it is producing something which looks a little bit sensible. Have I got the decompression code right? Yeah, seems to be. It's not a signed issue, right? Let's just tidy the code a little bit. I don't want to have to keep on doing the current map byte anded with 1f, right? Well, inside the while loop, we'll just do that once after it gets read. Look, I'm an idiot. I've set the map width to be 256. It's not. We're using 4x4 tiles, so actually it should be 64. 256 divided by 4 is 64, and the height should be 16. 16 tiles now rather than 64 characters. So there we go. The map data should be 64 by 16, right? And there we go. If I have the right map width and height, then the map data that was decompressed by this code is correct. There we go. So it wasn't anything to do with sign of bytes being read in and stuff like that. Sometimes, in Java that matters. It didn't matter here, so we don't really care. The while len out data for the map data will also need to get updated. Need to update that. But yeah, let's genericize this code a little bit more by moving it to a function that we can call for all of the level values from 0 to 15 now. So here we go, we'll just reorganize this code a little bit. We'll call it, I don't know, extract level, we'll call it that. And then we'll have a parameter for the level number there. We'll get rid of the variable set there with 0 because we want to pass that in. We'll just tidy up all of this code. Ding, 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 ding. Shift it along because in Python, right, indentation defines scope. When I first started using Python many years ago, it was kind of like, well, okay, that's the way it works. Fine, lovely. I came from languages like C and C++ where braces were used for indentation and to define. Well, braces were used to define scope. Didn't care how you indented, right, your source files. It was the braces which defined program scope. So I was a little bit surprised when indentation in Python defined program scope, but hey, there we go. So let's run extract level for all of the values that we want. There we go. There's a little typo there. There we go. So let's run that, see what we get. And oh yeah, we have a little error. What is the cause of this error? Well, it's extracted the first two files. Oh yeah, that's right. Need to change this. We were trying to extract too much run length encoded data and it was whizzing off the end of the file data blob, which is great that Python was telling us that. Basically, it's a memory safe language. It didn't allow us to read off the end of the read file data. So yeah, we definitely need to know and to note down and make sure that we know that the map is 64 by 16 tiles, 256 by 64 characters, but 64 by 16 4x4 tiles. And there we go. That's extracted all of the levels from 0 to 14. Doop. I put range 15. That should be range 16. We'll change that in a minute. But there we go. If I now import the map data as binary map data, and we go to, there we go. There's the other map, which is using the tiles, but it's using the decompressed map data. And again, if we just import the raw binary map data using these map dimensions, there we go. There's the other map. So I think we successfully have a nice piece of Python code now, which extracts the RLE compressed map data from in the game. So I think we'll leave this video here. I think there's quite a lot of content already, and this video is going to get quite long. So I'll save that file as well so you can see how it looks in terms of tile data. But we have the Python code. We have the automated remote monitor in Vice to extract the character-based map data, which is certainly useful, but I think it's more useful to have the RLE map decompression Python code. We saw how the map data was being read for collision and also for the enemy to player targeting, which is really interesting. We had a look at how the sprites are dynamically updated for the animations, and we had a look at the screen split and also the 2-bit drive protocol. So if you like these kind of deep technical dives into Commodore 64 retro games, then please do consider liking or subscribing to my channel. And if you really like the content, then please do send me a super thanks. They are very much appreciated. Thank you very much for watching. Take care. Have a great day or evening wherever you are.